Hello, everybody. Thank you for joining us and welcome to the second part of our virtual workshop on financial mathematics and stochastic analysis. In the first part, we had two very nice talks given by Tomoyuki Shiba from the University of California, Santa Barbara, and Isabel Figueroa Ferretti from Universidad Pontificia Comillas. Today, we have the honor to present Ioannis Paraskevopoulos from Bankia and Stefan Storm from the Worcester Polytechnic Institute. I want to give the floor to Carlos, who will introduce our first speakers. Thank you.
Okay, thank you, Mauricio. It is my great pleasure introducing you to Ioannis Paraskevopoulos. He's from Athens in Greece, and he currently serves as the head of quantitative analysis in Bankia, which is one of the main banks in Spain. He did his PhD in London, and now he's both working in the banking industry and also participating as a researcher in the group of quantitative finance at ICADE, part of the Universidad Pontificia de Comillas, here in Madrid. So please, Ioannis, when you're ready.
Yes. Okay, thank you very much, first of all, to the organizers and the very Mauricio and Carlos, and in this top event. And thank you very much the two speakers yesterday that they gave us a very exciting talks and aspects of the economic analysis. Now, I am in this talk, I'm going to speak about our joint work, a market approach for convergence trades with my co-author, Isabel Figueroa Ferretti and Tao Tang. I will be the talking today for them. Let's see the agenda for today. It will be a motivation. I will give first of all some motivation of the problem and how this is structured. Then we'll go on to give a summary, an early summary of the contributions of the paper. I will do some literature review, basic literature review on this, to place you in the literature. Then I would go on with the model and move on to the links of the spread options and optimal portfolio weights that I will be talking about. I will offer empirical results, and then I will move on to conclusions and close this presentation. The motivation, it's a bit blurry, but basically the idea that any investor would, a problem rather that any investor will face is from a cloud of available assets, which is there, the blue shaded area. We like to create an optimal portfolio that will generate profits and be stable enough, sucking information from that cloud of assets, with some sort of filtration that she has to apply to move from one area to another. Okay. How these kind of portfolios can be built? How can we fill up that white space with some portfolios? How what kind of dynamics these portfolios have? How these portfolios could be managed? And how we can use market data to identify and reprice our portfolios. Basically, the contributions are summarized in this slide. Will be moving. It will be moving from the P measure to the Q measure, and the initial filtration would be the benchmark model, would be the classical cointegration in the empirical work, the classical cointegration analysis that will filter certain assets from the blue area to the white area, to the white area, we will link that we will try to do a portfolio maximization of the expected utility of the portfolio and link that to the stationarity conditions of the continuous model and the option theory, especially the spread option. The literature review here. Here we have the main papers. I would say there are plenty. It's very vast literature, but most part of the literature has been in the statistical arbitrage models, and usually the hedge fund models, etc., trying to understand what these profits mean and locate these profits in the area either of mispricing or risk premium. That the risk premium that any investor would need to be compensated for any risk factor exposure that he would face in his portfolio, right? I would say that Gatef and Getzman and Andrade and all and Bunz y Prado have identified that, have linked the arbitrage profits to the variation of the risk premium, and in fact that it is a latent dormant factor that accounts for all these demand and supply balances that there are in the market, and they are picked up by the mispricing, and they will not go away if we discount the usual risk factors known, either the Fama Friends factors or more extended list of factors like, for instance, Bunz and Prado is using. They will not disappear. If anything, they will be stronger. Jurek and Jan and Liu and Timmerman have used the continuous kind of setting to approach cointegration in some sense. Jurek was the early paper there that it was just modeling the cointegrating error, one continuous equation, and then using some sort of utility function assumption in order to get the optimal strategies in the portfolio. Liu and Timmerman, on the other hand, they went a little bit further. They developed the dynamics of each asset involved and benchmarked it against the portfolio CAPE model. And they also used some sort of utility, some preferences for the investor in order to perform the portfolio maximization. Johansen and McGrabe. Johansen is the classical cointegration paper in discrete statistics, and it's been used extensively for filtering out information from the cloud of different alternatives. McGrabe is the link we do. It is an option, is Black-Scholes type of option pricer for exchanging one asset for another. And what we're trying to argue here is that the long-short strategies that all these papers refer to are the most sensible and most stable way to build portfolios. Arkigner and all 2012 have used the hedging argument that we can use one asset to hedge, cross-hedge, in fact, another position, a position we have on another asset, as long as the difference is stationary. De Miguel has De Miguel 2, Hirschfire, and MAD 2017. They have used the potential of De Miguel has spoken about the The information we can get from using market variables, as opposed to historical measures of mean or volatility that usually underperform in crisis periods. And two, with a recently published in the Journal of Finance, this is an old one, but it's recently published in the Journal of Finance 2020, they established that the long short arbitrage profits are basically is the factor that links the mispricings with the risk factors, with the risk premium factor literature. Figueroa, Ferretti, Paraskevopoulos and Tang 2018 have proved that actually introducing the classical pharma French factors only strengthens cointegrations, strengthens stationarity, and doesn't reduce stationarity. I would like you to, in this point, although I will be speaking about asset Y and asset X, you should be also thinking this as the total longs and shorts of a portfolio. It is the same analogy, right? The model setup. Okay, we have here, let's define our world. At this moment, we have a deterministic bond, which is the alternative asset. I have two risky assets, Y and X. I will be taking long position in one, short position in the other. But as an investor, I would like not to allocate all my wealth on these risky assets, but also to potentially allocate money on a safe asset as the economic conditions change. Here I would write down the stochastic evolution equations for this, which are basically OU type, that can potentially, as you can see, the main difference from the usual log normal processes is the lambda 1 Z and lambda 2 Z that they get on the drift. And then we define Z as the spread of the log spread of the two assets, right? Where mu's are the means and sigmas are the volatilities, and the individual shocks to each process. We expect that if the evolution of one asset is mean reverting, then the lambda 1 or the lambda 2 will be significant. But when they are both significant, they have to have opposite signs for the error to be stationary. Or if one, or at least one, should be 0. And it is, and the other one simply follows. Okay? So this setup is trying to emulate, if you want, the usual VECM story of how stationarity is maintained. Here we use the mean reversion property of stationarity. Now we write the dynamics. Here we have the errors, the shocks in each asset are correlated. And the evolution of the spread is given by this OU process, whereas as alpha is just the sum of the mean reversion speeds, and then is the spread of the drifts and the volatility of the spread, the total volatility of the spread. Now, in a traditional setup, we would like to build a portfolio consisting of these two assets that have all these dynamics that I saw up here on this on this portfolio, subject to some weights phi 1 and phi 2 and phi 3. Here we talk. Here the wealth is distributed to the three assets. So phi 1 plus phi 2 plus phi 3 is equal to 1 as such. And what it would be looking, the investor, is to maximize the expected utility of that portfolio, subject to some initial value of the portfolio, for his time horizon, right? I don't provide the actual, I provide only the solutions in these presentations, but there is a paper, you can go and check it, and probably you will see how these things are derived. This expected maximum, the V function then is the maximum expected utility of the portfolio, and that will determine the optimal weights phi 1 and phi 2, which will be a function of the first and second moments of the V process. As theta, we define the risk premium, or if you like, the relative risk premium, or the idiosyncratic risk premium as such. And the problem we have here, as it is, and this is how the literature is moving about, is what do we do after this point, okay? We don't know what the V function is, per se. We know that we know what depends on, but we need a functional form for that. Here, we think that actually the investors, if we have two investors and they have two relative accounts, is basically, this is a game of continuous trading in the long and short of exchanging of P for Q measure. P is your personal view, your phi view, and Q is what you can trade in a market. And this investor will only participate in the game, obviously, if he expects a positive premium for this investment. In other words, he will participate in a game of max y minus x and 0%. Our way, recognizing that we have that the long spreads, the longs and the shorts, it is a continuous interplay of the P and the Q as such from the two different accounts. I see the accounts in one way, the market will see in a different way. I believe I can make a profit from it, arbitraging the low value or the high value of the market to get my view and get my profit. So I would be looking at a spread-like option per se. Even without going through the maths, it seems logical to believe that we don't just go infinitely low, infinitely short, or infinitely long, because we try to keep our portfolio stationary. We will be subject to our optimal portfolio selection. Let's write then my portfolio, my hedging portfolio, DP, and some sort of a payoff C, Y, X, and T. That will be some sort of option value that after some simple use of Ito's lemma, we go on and we see the evolution of that payoff subject to the volatilities and the underlines. And we end up we end up with the solution for this option that is given as a function of the cumulative D1s and D2s, the typical similar black Scholes stuff. And the deltas, which are the delta Greek sensitivities of that option C, will be FD1 and minus FD2, which it follows that the optimal F1 and delta will be the delta Y, and the optimal F2 will be the delta X. I don't give here the derivation of the spread option as such, but I have that in the paper. Is a bit lengthy. These are the optimal. So what we suggest there, with the first glance, is that the V function is the maximum expected value, expected portfolio value, is equal, or if you like, has a good candidate, the spread option function. Okay. So we can write the maximum expected utility to be equal to the solution of the option pricer, and especially adjusted by the deltas, the delta position. Now we can parameterize all these parameters to get the actual fee values, the optimal fee values, which are related to the market values directly in such a way. As you can see, the VP will be the delta of the portfolio, and that will be just the spread of the deltas. The VPP will be the difference of the two gammas, the gamma sensitivity, I mean here. That will be also the VPP would be also the maximization condition. And then we have the cross derivatives on VPY and VPX, which is just the gamma spreads adjusted by the proportion of the two assets. All these are observable in the market. So using the formulas for the delta, for the gamma in the black Scholes environment, we can identify the VPs and the VPPY in the VP. As you can see from here already, here is like we have two digital options, basically. This is a digital for Y long, and this is a digital for X. So basically, taking a position in a portfolio is a digital position. If you're going long in one asset, short in one and another asset, the long asset will pay only if you are interested, at least, to pay only if it's positive, and the other one will pay one if it is negative. These are digital positions. Now, me as being a risk-averse investor, I know that these digital positions, I have to hedge that particular strikes, which are problematic because we have a highly discontinuous point here and a high uncertainty. As a risk-averse investor, I have to trade, I have to take the position, I have my view, I have my phi that I actually adjust my expected one, I adjust it according to the market variables, and I will move to hedge that strike, that particular strike, with a range of strikes that as close as possible as they are. The spread option will be replicating exactly the digital option as such. So we have these overheads, which gives a premium for the additional risk that that the investor will face by investing this money to one asset or another. A byproduct, although I don't offer calculations here for this thing, a byproduct is the early exercise. We shed light on the early exercise cost as been discussed by Ioannis Paraskevopoulos back in 2010, whereby the investor, although the idea is that the investor has his investment horizon, okay, it says, let's say that is 6 months, 1 year, but in between now and that period, maybe sees the potential of a big profit, not as big as possibly could be if he had waited until the end of the investment horizon, but big enough for him to consider, given that to obtain the other performance has to sustain more risk. So instead of sustaining more risk for a higher performance, maybe he decides to grab whatever big risk, whatever big payoff there is at this moment, and close the position. Ioannis Paraskevopoulos back in 2010, they have calculated that in the American setup, and continuous exercising dates. And we had this depending the cost of this suboptimal exercise in your portfolio was down to, it was based on the American gamma, the gamma of American option, which obviously is not observable and is very much model-based per se, subject to the dynamics you assume for your underlyings. We give light there, we say that, well, when I see that it's coming possibly a big profit on my side, and I will write to exercise is like facing a digital option, which is, again, I will try to calculate the cost of that exercise like if I was hedging it with a spread option, right? So I know the cost of that because that will be the difference of the two gammas. So in some sense, we give light to that problem and make it substantially easier to calculate some potential early exercise opportunity. Okay, the summary of the model that I went very quickly through gives us this picture more or less so far. Okay, if we have a cloud of assets, we have moved from a cloud of assets to this area that has many little blue balls there. For that, we have to move from the P to Q measure. This is eventually is going to be a trading portfolio. The first selection we have done, and that we use it as a benchmark, is with Johansen selection, so stationarity, three-step process to check and verify each combinations of the cloud members to form these pairs, and then we use the stationarity approach, and that will depend on some optimal phi's. We have maximized the expected utility function, and then we have used our model to determine stationarity with this simple condition alpha greater than 0, which is the sum of the lambdas, as we remember, and parameterize those for the empirical stuff through the digitals that we can get volatilities in the markets. These Black-Scholes, adjusting the Black-Scholes positions to get the required spread options valuation. In the empirical evidence, we have put at play all this game. So far, what we know is that our portfolio has to be stable enough and make profits with no substantial losses. So basically, it has to have positive skew per se. That is by expectation. Let's get some assets. Here we get the Dow Jones Industrial Average. We get historical in all companies. We start from 1997 until 2015 or so. We do this exercise. We do two different tests, two different subgroups, one with cointegration and one with our stationarity. Cointegration, I remind you, it is the three-step process, well-known process implied by the VECM formulation. And we create our first cloud of non-optimally mixed pairs so far. So what do we get by doing that? We get something like that. We see the maximum. This is a rolling exercise that we do all the time. This is very much out of the sample. So we're talking about the first 3 years, 97 to 2000 has been used for estimation, and then every 6 months was an out of sample, right? So to calculate the variation of all the pairs, one methodology like ours would produce the maximum number of pairs in the portfolio, the assets, and the maximum implied and minimum implied pairs in the portfolio by Johansen. We see there about the maximum is about, the mean is about 136 pairs. The Johansen is substantially lower. We have 185 maximum. The maximum with Johansen is very similar, but the minimum is, the minimum is substantially different. As you see, there is a big difference between the two portfolios. One giving 70 and another one giving 15. We calculated the mean reverting speed in many different percentiles, so to get a better picture of our lambdas and the Johansen's method. We see that the numbers are pretty similar per se, and the same goes with the volatility. The two models produce the same volatility. I have to say that I don't present in this paper the maximum likelihood estimation we have done to get the parameters estimates of our continuous model following the literature per se, but also is helpful once you don't have market information for some reason and you want possibly to use historical data to calculate your weights. So just with this, we see that the two models are behaving in the important part of the process. They behave similarly, and the estimated parameters are very similar to a certain extent. So we're talking about the same thing. Let's see some profits. How this continues. Long and shorts, weighted by the deltas, the positions that we take in each one, has performed out of sample, of course, against the alternatives. Here we have the mean of our model is about 11% per annum and that would be 1.01 Sharpe ratio. The Johansen is 0.921 and 0.8 Sharpe ratio. The market portfolio is 0.43, 0.3, sorry, with a 0.22 Sharpe ratio, and the delta neutral, which is equal weighting on the assets, would be, which is a very standard approach in the pairs, will be with a 0.68 Sharpe ratio and an average profit of 0.7. Let's talk. I'm sorry. Let's talk about another empirical test that we have done. We try to look at crisis periods and non-crisis performance to see how the model performance of the weights and the optionality that we give to the story performs. And this is very relevant slide for the COVID that we're going through. It's a special crisis period too. And according to this table, what we would expect to see is big profits if we were implementing a strategy like that. We have different companies are affected in different ways, so the relative liquidity changes and limits to arbitrage exist. Therefore, there is opportunities to make profits. And this is what's happening. This is what we see. We see that this period, the 2002 is the dot-com crisis. We see that we do 19.62% a year with a very high Sharpe ratio. And also the global financial crisis, 2007, 2009, too. Compare those profits in all models as such, comparing to the non-crisis periods, which we're talking about the January 1st, 2003 from until December 31st, 2006, January 1st, 2010 to August 31st, 2015. Our model almost it produces a healthy 5% a year with a Sharpe ratio of 78. And here we're using the same. We have calculated all these tables using in our model implied portfolio market volatilities for it. And here is what we're going to be using historical volatilities for calculating the same weights. And you see the crisis, non-crisis distinction. This is 7.3% per year with a Sharpe ratio of 72 between 2000 2002 and the global crisis. We averaged 14.08 with a 0.93 Sharpe ratio. In the non-crisis years, 4.1. So obviously it takes an advantage of the stationarity argument that which is persistent in certain areas of the cloud, as opposed to others that become more erratic and more volatile. Here, allow me to show you the main two groups according to the filtrations at least we have done. The market implied portfolio, which is ours, the blue line, and the Johansen portfolio that typically is built in the pairs industry. in the portfolio building. You see that until 2002 the profits are very high. They're going steeply high, and then as the non-crisis periods comes, is a little bit flat, but still not be a good healthy portfolio. The two lines are pretty similar. So basically we model the same thing, but allow me to say the drift is different to Johansen, which Johansen is a bit, it's not very clear for which drift the critical values are appropriate per se. And you can see that in 2008, it gets a big slump, the portfolio value for the Johansen type of approach, whereas ourselves, we actually going upwards in the cumulative during that period, strengthening our profits, winning more per se. And after 2009, there is a healthy difference, avoiding all the big slumps, as you see, a very smooth payoff as such, as opposed to the Johansen, which will give you big dips, which means losing a big part of your portfolio in just a small period of time. Okay, we have given certain formulas there very quickly. I have to admit about the risk premium, the theta z of the portfolio, and the delta of the portfolio, the exposure for the Dow Jones Industrial Average, for long, short, how this thing would look like if I plot it. How would they look like? Would they pick up if it, that is a sanity test per se, but it is very, very important as an indicator and where the market stands. The theta and the delta should give the variation we expect in crisis, non-crisis period, intervened or non-intervened markets. I will show you the graphs now. The delta is calculated like that, the spread of the two deltas. And here is the theta, this thing. Okay, what do we see here? We see increased risk premiums all the way up to 2002, that we have the dot-com crisis, then reducing. You can see that as an indicator of mispricing. How the mispricing, if you like, the mispricing that gives you the opportunity to make money, how the market was mispricing during the crisis periods, and that's why we see that we make profits. You see how the market will be more efficient after the intervention of the central bank that changed the rules in the banking sector, and they allowed to use their own risk models and basically no limits in the short positions. And you see how much increased the efficiency in terms of this pricing. And then how the 2002 turbulence and another quantitative easing reduces mispricing. Two different strategies observed from the central banks. One here is to allow more flexibility in arbitrage and the leverage, and use their own risk models and more dedicated pricing. And here is no many restrictions on the short, but we have a lot of cash being given in on the other hand. Here is what Isabel was talking about yesterday, the 2014, not only the oil, it was spiking up, the CDS, but also the risk premiums on other assets, like the Dow Jones was spiking too. So we can say that the theta is very reasonable, and this what shows us more or less the mispricings or the risk factor, the risk factor premium, how it moves along the time. And the delta of our portfolio, the exposure shows exactly that. So how much exposure do we, how much delta do we have to put in our portfolio? Well, a lot during the dot-com crisis. Then the first regulation, 2004, reduces more efficiency, reduces the deltas needed. 2008, we go big again, and now quantitative easing. Here it goes up and down because it's a rolling sample, so it's every 6 months more or less. Okay. I think, concluding, more or less what I've tried to convince you is that it's good to build stable long short portfolios based on stable pairs. The spread options is a candidate maximum expected utility function. The delta optimal weights for asset allocation is the appropriate optimal weights to use. Optimal strategy is associated with exercising digital options. Exercise of a digital option which pays only if the price of an asset is above a certain level. Profits are higher in a crisis period. Market volatility is better predicted than historical volatility predicting the exercising probabilities. And with that, I think I finish and ready to accept any questions. Thank you very much.
Thank you, Ioannis. Thank you very much. Well, we can start with the questions. Let me ask you the first one. We have to implement this strategy, we need two correlated assets. And my question, I have two questions.
Sorry, Mauricio, I don't hear you very well, sorry.
Okay, yes, to perform, can you hear me now?
Yes.
Okay.
Yes.
Okay. To perform the strategy, you need two correlated assets. And my question is, if in crisis, these assets still well correlated, and why could you say, what could you say about why is more profitable in crisis periods?
It's more profitable because can you put the volume down, please? It's more profitable for we have a shift in the relative liquidity of the two assets. When this shift of the relative liquidity is stationary enough, is not moving apart, that we can use to make a profit. That gives you the gap necessary to intervene in the market and get one position versus another position. When we have when we are in stable, when we are in growth periods, when we have no crisis periods, market efficiency is of a higher degree, meaning that the relative liquidity is more or less stable. It doesn't give you those seats necessary to intervene in the market and go and buy or sell.
Nice. I may add, during crisis periods, because of the higher correlation, there is stronger mean reversion. So although there are restrictions to arbitrage, once you manage to arbitrage, the mean reversion is stronger, precisely because correlations are higher. So that's also the intuition behind.
Thank you, Isabel. Well, if you have questions, any attendee or panelist? Okay, I see Carlos, there is his hand. Please, Carlos, and you have your microphone turned off.
Now, thank you, Mauricio. Yes, Ioannis, I have a question related to the models, the stochastic differential equations for the two assets, because these equations, they don't fulfill the requirements of the classical existence and uniqueness theorem, right? You have logarithms involved, and although I can believe that the solutions, they don't blow up in finite time, you need a control so they don't reach zero, right, in finite time. Otherwise, you lose the existence of the solution. So, well, I wonder how you control this.
I think once the first and the second order conditions are justified, I don't see how this can be degenerating per se. This is a model. Sorry, oops. This is a classical U model that actually, if I would see it like that, if if the lambda is equal to 0, then we have a standard Brownian motion. If not, we have a mean reversion. So if we have a standard Brownian motion, then we'd be exploding per se at some point with the square root of the volatility. If not, we have a volatility time decay. So I don't quite get in what sense we vanish, to be honest.
I mean, so you mean it doesn't get to zero at any time with probability 1, or
No.
I don't know if I got your answer, or
sorry.
Yes, I don't know if I. So the solution, it never gets to zero, right?
Never.
Okay. Okay, thank you.
Thank you.
Very good question, Carlos.
Thank you. Someone else have a question or a comment? Okay, we have Eduardo from the attendees. Let me allow you to speak. Please, Eduardo.
Okay, thank you, Jan. It's very interesting to talk. My question is very similar to Carlos' questions. The basic stochastic process that you formulate there with the lambdas. Tell me, is this your development, or you're taking this from somewhere else? I haven't seen that, because that's a very peculiar stochastic process.
It is.
So
it is my development.
To make me give me the intuition about that, because you're assuming mean reverting stock prices. That has implications for market efficiency and so forth. Give me a little more about that, Ioannis.
Yeah. Thank you, Eduardo, for attending, and thank you very much for your question. Let's go back to those, so we know what we're talking about. Those.
That's it, yeah.
Yes. The literature, the most similar thing, Isabel, can you take the volume down? The most similar thing you can find in the literature maybe is the Timmerman 2014 setup. This is an independent developed setup. I found about Timmerman once I have developed that. And so let me say it's quasi ours. It's not 100%, but I'm sure I cannot think that nobody else has spoken about this formulation. To me, seems like a U process. It's like a mix or U process. So it's not. I think I try to emulate how I built it. Is trying to emulate the movement of stationary. What it means for two assets, the spread of those two assets, which is this here. What this to me, what it is to be stationary? What does it need to have to be stationary? And how do they have to move in time? In a classical integration, we know that one is overvalued or the other one is station, it hasn't moved or it has moved down, and we go short this, long this. So that movement required some sort of mean reversion with opposite lambdas. For instance, my difference, big difference that I have with Timmerman that I've studied later, is that Timmerman doesn't make any assumption on the sign of lambdas per se. So for him, they can go both up or both down or against a benchmark market, which I believe is the other thing that I'm not using here. The benchmark market needs to be incorporated in order to be able to make such a statement. All of the three assets have to be cointegrated, the market and the other two risky assets per se. That is the difference I have with Timmerman, but the way I have constructed conceptually in my mind, the equation 2 and 3 was just to capture this movement of up and down of some sort of equilibrium level of the equations. And if that relationship existed, and Y's process was actually conditioned partially by the X's process, then it would revert to some sort of spread error of the two.
Yeah, but these are time varying expected returns.
This is how I built it.
In this asset.
And given that I saw some similarity with Timmerman, and given that we constructed the actual portfolios with those relationships, and given that it makes sense to what we get and how do we compare, especially with a traditional and accepted way of how cointegration is modeled in the discrete time, at least by Johansen. I believe that I emulated that movement of stationarity between two spaces, the longs and the shorts. No?
I want to thank Ioannis for your talk. Thank you very much. And remember, our attendees, that we can continue with the questions at the end of the workshop.
Thank you very much.
Thank you very much.
For everybody. Thank you.
Thank you.